Okay, so my talk is on cycle-accurate 88 emulation. It's a very broad topic, so this is kind of more of a high-level overview of how I accomplished it. Just a show of hands, how many people have you even heard of MartyPC? Oh, quite a few. It's a pretty new emulator. I've been working on it for the past 2 years. Before I begin, there are a few people I'd like to thank. Ken Sheriff, especially. You probably know his name. He's here at VCF. I think he's doing a roundtable on Sunday. He's got an amazing blog where he does gate-level analysis of decap chips. And it's just absolutely fascinating stuff. And of course, a lot of his research into the 8086 was applicable to my emulation of the 8088. The other person I'd like to thank is Andrew Jenner, known as Re-Enigni. That might be a name some of you are familiar with. He's a legendary demo coder and the developer of the XTC-E emulator, so he's a friend and the competition. But he also decoded the 8088 microcode, which was a big step in allowing this to even be possible. And then finally, Andreas Johnson, the developer of the virtual XT emulator, came up with the idea of hardware validating an 8088 emulator, and I liked that idea, so I shamelessly stole it. So before we talk about the 8088, we need to talk a little bit about the 8086. It was introduced in 1978. It was Intel's 16-bit follow-up to the 8080 and 8085. Despite being a 16-bit chip, it had a 20-bit address bus. So it could address 1 megabyte of memory, but it did it so in a rather controversial scheme called segment offset addressing, combining two 16-bit registers with a 4-bit overlap. And this would annoy programmers for the next decade. It did come in a small DIP package, which was attractive to integrators, but it did mean that your address, status, and data pins are all multiplexed, so they're only valid on certain cycles, which is annoying to deal with a little bit. So the 8088 is basically an 8086 SX. It's got a half data bus, so only 8 bits. But they did kind of slick thing with it. They modified the bus interface unit on it to transparently split any word transfers from your program into sequential byte transfers. So it's completely software compatible with the 8086. It's just slower. But it was also lower cost, so IBM picked it to be in the original IBM PC and the original XT. Even though the 86 is the more famous chip, it was really the 8088 that was in the birth of the PC. And these chips had some pretty big innovations. I couldn't find evidence that they were the first chips to have all these, but they were at least one of the first. The 8088 has a microcoded instruction set. What that means is that the externally observable instructions are actually implemented with smaller, more atomic operations encoded in ROM. And these can be complicated little programs, almost Turing complete. They can do flow control and subroutines. And this allowed instructions to be implemented that didn't really have any support in Silicon otherwise. Like you could have multiplication and division, even though the 8088 had no dedicated Silicon for it. You ran the whole routine in your microcode, which explains why those instructions were rather slow. Talk about the split brain design here in a second. The instruction queue is also interesting. These are one of the first chips to do instruction prefetching. So they would read ahead of the currently executing instruction. While that instruction was executing, read the bytes for the next instruction. It's old hat now, but that was kind of innovative at the time. Not a huge queue there. It's only 4 bytes on the 8088. So the 8088 has a split brain. It has 2 main functional units, the bus interface unit and the execution unit. The bus interface unit is what you'd expect. It handles the bus, it executes bus cycles, and it's responsible for that prefetching process, which it does pretty much on its own whenever it feels like it. One important thing is it does have a dedicated adder for calculating addresses, and that'll be very important in a second. The execution unit, meanwhile, is responsible for executing the microcode and doing ALU operations. And the important thing to know is if it needs to write an operand or a result back into memory, it has to make that request to the BIU. So it can't directly access memory. Here's by the way, I need to thank Ken for that photo. I did colorize it a little. You've got the BIU at the top, so it's really more like 1/3 of the chip, but logically it's a split. And here's the logical diagram. What you might be interested here is the dedicated ALU for the microcode, and then up here we have a dedicated adder for the BIU to calculate addresses. So we need to take a segment and an index register, put them in our adder to get our final 20-bit address. So we need to know a little bit about the 8088 bus cycle, because this ends up being one of the cool things that was discovered very recently. The traditional bus cycle is given as 4 cycles. That means every time the CPU needs to read or write to memory, you're going to spend 4 CPU cycles doing it. And these are labeled as T states, T1 through T4. The important ones are T1. That's the cycle on which the 20-bit address is placed on the bus. And then on T3, that's the cycle where normally the value to be read or write is put on the data bus. Same pins, just the context of what the bus is changes. And there are 8 different bus cycle types. These are encoded in 3 status lines in an octal format. The most important one here is the code access bus cycle type, because that's going to let us control the CPU remotely, which we'll see here in a second. Talk a little bit about instruction prefetching. I mentioned it's an automatic process. The bus interface unit just does it whenever it feels like it. If there's generally room in the queue and the bus is not otherwise occupied, it will attempt to fetch a code byte. And it uses these code fetch bus cycle type that we saw on the previous slide. At T4, that result of the fetch is put into the queue. Now, prefetching is a bit of a misnomer because everything is fetched. You cannot execute instructions directly from memory. They have to go into the queue and be read out, even if the queue is empty. That has to occur. And if the execution unit and the bus interface unit argue about who gets the queue, the execution unit will win, although it will take up to a cycle to stop the prefetcher. There's a lot of data on here. You don't need to know all this. The main thing is that these green 24 different indirect addressing modes, they're all implemented with microcode, and they all have a slightly different microcode program. That means that all your instructions take a variable amount of time to execute depending on the addressing mode. So that's fun to emulate. So now that we know about the 8088, let's talk about emulating it. What does it even mean to be cycle accurate is the first question. This is a contentious question. I asked in the EmuDev Discord, and there was a little argument that ensued. But my definition is that it generally refers to the granularity at which an emulator can generate or respond to system events. And you can compare that to instruction accurate, where an emulator just runs an instruction, assumes that nothing bothered it, and then continues. So if you have an instruction accurate emulator, your loop might look like fetch an instruction, just read it from memory, decode the instruction into whatever format you want, and then execute the instruction. And then you return some cycle count. That could be just made up, an estimate. It could come from a table, something you read in the Intel manual that's probably totally inaccurate. And then you advance the machine state. So you take your bus or all your devices by some function that returns time given the CPU cycle count the instruction took. But there's some problems with doing that. There's a lot of things that can happen while an instruction is executing. Like the bus interface unit can go, oh, I want to prefetch, and you have to account for that. You could run into wait states. Some devices like the CGA card don't even have static wait states. It depends on when you access them. You could have DMA at any time. And on the IBM PC, DMA is going on all the time for DRAM refresh. You could have bus mastering if you're emulating an FPU, if you're that sadistic, you could have a request come in. And you can also have a hardware interrupt or NMI, rarely. On a 5150, that's a bad thing. That could happen on any cycle. And it turns out even though Intel says that interrupts are checked at the end of an instruction, it's actually 2 cycles that can occur on some instructions if they have an NXT flag. Not need to know that, but it does matter which cycle you check your interrupt on. So the main thing is that on the 8088, cycle counts are impossible to pre-calculate. And I have this poster board. This is a histogram of the entire instruction set. You can see if there's one line, that means one cycle count per instruction. Some of these have 4 or 5. Some of these down here, they look like crazy graphs, like there's mountains and peaks. Those are those division and multiplication because they're executing loops. I'll have this in the other breakout room if you want to take a closer look at it. But it just goes to show how you can't just look at it in a table and see how, oh, this instruction takes this number of cycles. And this isn't even accounting for the prefetch queue. So you have to make all these variables and multiply them by 4. So a cycle-accurate emulation loop is much more complicated. It's the same basic steps of fetch, decode, execute, but you have to go through the bus interface unit for each step. Because even when you fetch your first byte, the bus interface unit has to honor that request, get it into the queue, and read it back out. One thing to note is that the 8088 does not immediately fetch immediate or relative operands. That was a fun thing to discover. Those are done specifically in the microcode. So if you think about it, the decoder on the 8088 really has no idea about immediate operands. So there's some considerations and some optimizations we can make. Obviously, we can't just tick the system, the entire device state, every cycle. Imagine drawing a CGA card 1 pixel at a time. But not every device in the system requires cycle accuracy. It's common to do your video device by scan line, for example, if nothing is going on. System events are often predictable, so a scheduler is a very common technique in emulation. So I can cheat and I can look at the timer channel 0 value, and if it's got a number, pretty high number in there, I know I don't have to worry about timer interrupts happening at any time. And user-generated interrupts can have some latency to them. No one's going to notice that your key press was 3 microseconds late. And you can synchronize only when needed. So if you do want to have a cycle-accurate CGA card, you can wait till an I/O or a write to the video RAM happens, and then you can tick the card up to that exact cycle and then perform the read or write. Cycle accuracy implies but does not guarantee correctness. I don't claim to have made the first cycle accurate emulator. But what I tried to do is make mine cycle perfect, at least to a certain degree. But how do we know we are cycle perfect? How do you know that your emulator is doing exactly what a CPU does on every single cycle? We have the opportunity to use CPU test suites. Tom Hart, maybe some of you have heard of him. He's got a lovely collection of CPU tests. If you're making a Nintendo emulator, you just run those and you know your CPU core is perfect. Great. 8088 didn't have any. So we needed some other way to validate execution. But it's been 45 years since the release of the 8088, so it is a valid question as to why this wasn't done anyway, just through brute force. One of the problems was the microcode was a black box. You have loops and flow control operations, and these all complicate timings. You look at like division down there, you could make a table of it. The Cordic algorithm was known, so you could try to like plug in the operands and get the cycle counts out of that, but it was very hard. We know that the instruction queue, the prefetching, the different addressing modes, the asynchronous BIU, all of that made calculating execution time very difficult. But maybe the main reason was that emulation was just considered good enough. The early PC was not really known as a gaming machine, even though there were a lot of good games for it. You could run Big Top by Michael Abrash by dialing your DOSBox cycles down to 300. It would run acceptably well. And even back in the day, people upgraded their 8088 to a V20 or overclocked it with a little add-on board. So even back in the day, being slavishly 4.77 megahertz was not always the goal. But this is my favorite opinion, my hot take. I say no demo scene means no challenges to the status quo. If you look at the emulation scene for the Commodore 64 or the Amstrad CPC, we've had cycle-accurate emulators for those systems for a decade now, because they have a vibrant demo scene. We just had, what was it, Revision, the demo competition? Brand new Commodore 64 demos released just this month. So we didn't really have any demos for the PC until 2015. Anybody heard of this? 8088 miles per hour was released. This was the first full-length demo scene production for the original IBM PC. Runs on an unmodified 5150 with a CGA card. And its main claim to fame is getting 1,000 colors out of the 16-color composite CGA mode, which is pretty impressive. But it also just basically beats the hell out of the CPU. Before you even start it, it does a CPU test. It runs through pretty much every 8088 instruction, times the whole business, and yells at you if you're inaccurate. This is an example from DOSBox. Not throwing shade at DOSBox, but DOSBox does not attempt to be cycle accurate, and we're 32% off. Every instruction that runs in DOSBox is assumed to take the same amount of time, which is not how the 8088 works. But this is the real tricky one. This is called Kefren's bars. It's a standard demo scene effect, but this was the first time that racing the beam like an Atari 2600 was done on the IBM PC, of all things. This was an effect also made by Rianigni, and to show you just how brilliant a coder he is. Each scan line here has to execute in exactly 304 CPU cycles, no more, no less. Otherwise, you don't have those horizontal lines in the background. And this includes the DRAM refresh process, which is happening in the background all the time, injecting wait states. And every time he accessed the CGA card to read or write to memory, it gave him a variable, but predictable number of wait states. So he has to calculate all that into the 304 and hit it every single time. And if you're running this on real hardware that's not an 8088, your monitor will be very unhappy with you. So this was 2015. When this was released, no emulator could run it, but Rianigni had been working on his own emulator. They ported that to 86box, and eventually in 2019, 86box became the first PC emulator to run it without major glitches. That was 4 years it took. So I think this is hilarious that Rianigni broke emulators and then fixed emulators. I will give credit to Microcore Labs. They're also here at VCF this year. They have an FPGA CPU implementation that does very well on it. Not perfect, but very impressively well. So in 2020, Rianigni again, his name comes up a lot. He used die shots that Ken Scherf published, and he was able to extract the microcode ROM contents using Bitstract, I believe. And that would just give you a bunch of zeros and ones that you couldn't decode, except that Intel happened to publish a patent that described the whole format of the microcode, happily. They would learn their lesson and not do that ever again. So now, thanks to Rianigni, we have half of the behavior of the CPU well-defined. That's a shot of the microcode. That's what he had to decode. Good luck. And this is an example of the disassembly. I actually have the full thing right here in one poster. This is the full disassembly of the microcode for the 8088.
How many instructions?
512 words. Not all of them are used. The gray are kind of dead spots. They're 21-bit words, too, which is a little weird. But, I mean, it's microcode. You can do whatever you want. But that's just all the code for division specifically, so shows you how complicated that is. So now that we have the microcode, we just plug it into our emulator. We have a cycle-perfect emulator, right? No. Because the execution unit will say it reads and writes on a specific line, but the bus interface unit can be like, I'll get around to it. So instruction execution is not purely a function of microcode execution. So we were starting to capture hardware traces from real systems, real CPUs, and we're trying to figure out, we're plugging in the line of microcode that's executing on every cycle, and it wasn't lining up. Like this is a hardware capture from an Arduino. These pink lines here, these represent mystery cycles. We have no idea what's going on during these cycles. It's not microcode running. It's not the bus doing anything. It's TI idle states. We didn't know what they were doing. So a little sidetrack. It's good to know how we get hardware cycle traces. Andreas Johnson, developer of VirtualXT, pioneered this process, at least as far as I know. He came up with this little board, just a passive socket to GPIO adapter. And he wrote some really cool code for it, so it can set up an initial register state, it can execute an instruction, and they can dump the final register state. And he used this to validate his VirtualXT emulator. And I thought, well, he isn't trying to be cycle accurate because he's not insane, but I thought I could expand on it a little bit. So I came up with an Arduino version. Now this uses an Omega. There's two nice things about it. It's got a lot of pins, so I could connect literally every pin on the 8088. We can run the CPU in maximum mode. So it's the same mode it was configured in the IBM PC. And maximum mode just is a mode where it can use a coprocessor like the 8087, the floating point unit. But that gives us, it starts to advertise its internal state in that mode, which is very useful for controlling and seeing what it's doing. And we needed the little 82, 8088 bus controller over here, just for fun. And then once I got that debugged and working, I made a little hat, and it's sitting right here. It's to get the Mega on the bottom and the Arduino on top, and it's a real CMOS 8088 in there. And now we can take basically Andreas's slightly modified routines, but set up and read out the register state directly on the Arduino, so the host system doesn't have to worry about it. And then we can have a simple serial protocol that you can communicate with this thing as a remote CPU server. So we can just give it 28 bytes for our desired register state, and it will set it up for you. And you just tell it to cycle the CPU or read a specific pin, and you get everything back. So we can make a little routine that you can actually make a bash script, compile an assembly file, and then upload it to the CPU and run it and get the traces back. And how do we do this though? So remember that code fetch bus cycle. We know that is a signal that the 8088 is prefetching. So when we see code fetch, we feed it a byte on the data bus, the next byte in the binary. And we can emulate the address space in the host, so when it reads or writes some memory, we just give or save the bytes that come over the data bus. And by monitoring the state of the instruction queue, we can even determine when our little program ends. And so in maximum mode, we have these two states, QS0 and QS1, that tell us exactly what's going on with the instruction queue. They give us 4 signals. When the first byte is read, a second byte is read, or when the queue is empty, or when the queue is idle. That's kind of weird. Like, why is the CPU bothering to tell us this stuff in the first place? Well, the 8087, the way this was designed, is the floating point unit was basically watching the same instruction stream as the CPU, just waiting for an FPU instruction to occur. And when it did, it would just yoink the data out of the data bus while the CPU fetched it. It's very clever, but it just so happens to give us all the information we need to control the CPU remotely. Since we know when the bytes go in and we know when the bytes come out of the queue, we can track the queue contents, and since all instructions go through the queue, we can literally decode, disassemble the bytes into, or reassemble the bytes. So I thought I'd give you a little demo because I got this little guy hooked up. I might need to switch screens again. I am bad at presenting. do you switch screens on a Mac? All right. Yay. So just real quick, you press play, it's going to upload the code we run, and it's going to dump these cycle states. So each of these represents a single cycle state, and these are the 82, 88 bus lines, the bus status, the read and write from the data bus, and then we have some disassembly here, so that was an SPB instruction. And then it dumps the initial and the final register state for us. Sorry about that awkwardness. So we can build this into our emulator now that we have a protocol to use. All we have to do is well, this is what I did in MartyPC anyway. When I run an instruction, I record all the cycle states that the emulator generates, and I build a list of bus operations, reads and writes and such. And then I play that back to the CPU, and I record the same cycle states. And they should just match, right? If you have a bus cycle that's the wrong type, you fail. If your writes don't match your emulator writes, you fail. If your cycle lists aren't the same length, you fail. It's very easy to fail. And this is what this looks like when I fail. We've got the CPU, the hardware on the left, and the emulator on the right. And you can see I was a little too fast here, because there you have these mystery cycle states, these TIs. Didn't understand them at the time, so this is what happens. You just don't have the right timing, even though you have the microcode. And so this is good, but it's just a CPU on a board. The PC is a much more complicated beast. It's got all sorts of things going on. So it would be nice to capture the state of an actual running system. And again, the FPU comes to the rescue. Since it has most of the same pins connected physically to the CPU socket, we can just stick a little adapter in there. Rianigni beat me to this concept. Of course he did. But he also built a ISA card with a microcontroller. The only limitation is that it's very limited RAM, so we can get 2,048 cycles at a time. But he's got this hosted online. If you go to his server, you can upload a binary and just wait a minute, and you get a cycle trace back from a real IBM 5150 sitting on his desk. So I wanted to get entire captures of demos, so I'm talking millions and millions of cycles. 2,000 at a time was not going to cut it. So thankfully, commercial logic analyzers are now smaller than a deck of cards, and they can stream via USB-C, and you don't need any storage on them. I actually used one of Andreas's Pi 88 boards. Instead of a socket, I put pins on it. And I just flipped the GPIO header around, and it makes a perfect CPU socket adapter. I took that on a ribbon cable out of the case, and logic analyzer is this little black box here, and all these wires. Pardon the mess, I was just kind of attaching ground leads in a desperate attempt to make it not noisy. This is what you get out of the logic analyzer in raw format, which is pretty, but no use to anyone. So you have to write a decoder for this. Now, decoders, this is the SIGROC PulseView program. SIGROC is a great open source logic analyzer software. Decoders are built in Python, but it turns out we already have all the logic we need. When we built this board and we wrote the code for it, we had all the logic for decoding the pins. And decoding from a logic analyzer software is no different. It's like a player piano that's playing the pin state back to you, right to left. So you just use the same logic to decode the analyzer file. You just have to rewrite it all in Python. And so what that gives you is a zoomable and scrollable view of CPU cycles. And I'd actually like to show that to you because it's more impressive live. More awkwardness. Come back. So this is a cycle capture of a demo called Area 5150, if any of you have heard of that. And down here at the bottom, you'll see my 8088 decoder. And if we zoom in, keep zooming in, oop, there's instructions. So we see that's a jump. That's a empty the queue flag. So we took that jump because we emptied the prefetch queue. We can see the CSIP. This is very handy for following along with the disassembly in IDA Pro or GIDRA. You can see the individual T states. It's everything you could possibly want. And you can see, you can capture other things other than the CPU. I have the interrupt line, the DREC 0 line, so I can watch DRAM refresh DMA. You can even capture vertical and horizontal sync off the CGA card, because why not? Now, how do I get back to my... Sure, just do that. Sorry. Yay. I'll learn. I'll get better. I'll be better next year. So there's some funny thing. The 8088 had a final secret waiting for us, only revealed last year. And I thought I had discovered this, and I went back and looked at Ken's blogs, and of course he had discovered it first. But if we think about it, on T1 of a bus cycle, the full 20-bit address of the operand is placed on the bus. And we saw the little adder that it uses to do that. Well, this is a CPU that takes like 3 cycles to add 1 plus 1. So it's not getting that 20-bit address instantly. So it turns out there's 2 more cycles involved in a bus cycle. And Ken called these TS and T0. And I humbly suggest there's a third, I'm calling it TR, and that represents the cycle on which the execution unit requests the bus in the first place. So that means when the execution unit requests the bus and the bus is otherwise idle, it's going to take 7 cycles, not 4. So all those mystery cycles were the 3 that we didn't know about before. And you might be like, well, that's nonsense. You can execute like no ops back to back in 4 cycles. What are you talking about? Well, I'll show you. Here are no ops executing back to back, but you'll notice there's 2 pipeline lines now. So we have T1s through T4s executing back to back, but the 3 new cycles that we're now aware of are pipelined with the previous request. And as long as you have the bus active and flowing like this, you'll never notice that the actual latency or bus access time is really 7 cycles. So that's the big revelation. And to think that a 45-year-old chip still had secrets like this is pretty crazy. Also explains some things like prefetch aborts. We used to think that these 2 cycles here were mystery cycles. You just paid them as a penalty when you had to do a prefetch abort, and that's just how it was. Well, no, there's no abort penalty. The bus interface unit checks on T4 if there is a impending request from the EU, and it immediately switches to the EU. It's not penalizing the EU at all. It just takes it 3 cycles to get going. So we're no longer being penalized. The maximum delay, because it doesn't check on T3 to abort, it only checks on T4 to abort, so we can at sometimes pay 1 cycle penalty. It's not that much. Some assembly programmers in the crowd may know that the move SW instruction was much faster than move SB. Even though the 8088 had an 8-bit bus, you wouldn't think that it would have much of an advantage. You're still trying to suck bytes through an 8-bit straw. But the reason it's so much faster, not just because of reduced loop overhead, there's only 3 cycles of loop overhead, but a lot of it has to do with the fact that that second byte in that word transfer is pipelined, which is something we couldn't really explain until now. And it also explains why it takes a few cycles for us to wake from halt on an interrupt, because the interrupt is another bus cycle. And so it has to go through the same calculations. So I have some gifts for the emulator community. There weren't any tests when I started, but I used this little guy. I used 3 of them, actually. And I made a test suite. It's up on Tom Hart's GitHub, along with all the other test suites. So there's 3 million JSON encoded instruction executions for the 8088. So if you're writing a cycle-accurate emulator now, You have a test suite. You don't have to build a stupid hardware board and go through all the trouble I did. I also published a blog where I go over Ken's discovery, of the 7-cycle bus access time. And I basically have every example you would ever want where we had unexplained delays that are now explained by this new model. So I'm arguing there's no excuse not to make a cycle-accurate ADA emulator. There's only like 1 or 2 little minor details that are still yet to be explained, but you can do it 99% accurate. And I challenge anybody starting one today, go ahead and try it. You've got all the tools you need. And it just so happens that today, to the day, is the exact 2nd anniversary of MartyPC. So here's where I said, I think I'm going to write an emulator in Rust. And this is what the current version looks like. It's got a lot of useful debug displays. And I've got some stickers to hand out if you want some. Just come find me over there. How are we doing on time? Yeah. That's it.
How about giving him a big hand, because that was a wonderful presentation. So do we have any questions for our speaker? Yes, sir.
I saw you had an AMD 8088 on your Arduino hat there. Are there any functional differences between the AMD and the Intel? And then, I guess, same question with the V20.
So an Intel 78 version doesn't run under validator board because of the clock rate. There's a minimum clock rate. And it's interesting the way it fails. It looks like it's running perfectly fine. It will do EA address calculations, but if there's a displacement, it sets the displacement to 0. That's the only thing it fails to do. It'd be fun to kind of like try to program around that limitation. But the AMD D8088 is still an NMOS chip, second source. And from what all the sources I read is that there shouldn't be any differences, but it runs just fine. That's the one you saw there. I have a Harris CMOS version that's what I used to generate the test set. There are slight flag differences between the two. There's also lots of little differences, like the Harris will delay interrupt by 1 instruction after push of a segment register, which is a little excessive, because pushing a segment register doesn't affect the segment register, so why would you do that? Nobody knows. You'd have to ask Harris.
Anybody else? Yes, sir.
So that dovetails nicely with my question, which is, when you were running it on the Mega or something like that, do you have a rough idea what the clock cycle was? It sounds like it was very slow.
15 kilohertz.
Right.
It's a blazing speed.
And a similar thing, I guess it's the same thing. Going from NMOS to CMOS is not a trivial thing. Lots of stuff usually changes. How confident are you that the NMOS and the CMOS chips behave the same at full speed?
Well, the proof is in the pudding in what my emulator can run, I think. And it runs a lot of things very well. There is one thing I'm trying to figure out. There is one specific diagnostic who detects me as a Harris, although I'm trying not to. My emulator is trying not to be a Harris. And I haven't figured out what it's finding yet.
Huh.
But I do plan to test as many different models as I can and try to suss out those differences. So what I'm going to do is put the AMD back in, and I'm going to re-verify the test set against the AMD, and then any discrepancies between the AMD and the Harris I can document. I'd love to get the Intel 78 working. So what I'm doing is working on a new version for the Giga. Being that it's much faster, it should be able to clock the CPU at native clock speed, which would reduce that. So what we would have to basically give it the program to run, let it do its thing, and then get the dump it all from memory, because you can't just control it back and forth. Even over USB 3, it's not really, the latency is too high.
Have you looked at the RP2040? This is
Yeah, and the Teensy, I evaluated a lot of different boards. Really, the advantage of the Mega was I was lazy and it already did 5 volts.
Yeah. Yeah, that was the other big question. Fantastic stuff, thanks.
Anybody else?
And this is for the future. This is my board for the 286. We're going to have cycle accurate 286 emulation if I can convince Ken to dump the microcode.
Last call for questions.
I'm a user of the V20 from years and years ago, and this gentleman here asked you, like, did you ever have a chance to test out the V20 on your board?
Yeah, so the board is, I mean, you could put an 8086 in there or a V20. They're all pin compatible, basically. There's just a few little tweaks. I have to just change the code to read the 16 bits off the data bus. And I can actually use the same status line, the BHE line, that the 8087 used to detect an 8086 or an 8088 and just automatically switch my code depending on which one I detect during reset.
Did you actually put a V20 in there to?
No, I haven't yet, but I do have a V20 and I do plan for it, but 8086 is first, and then I'll work on V20, V30, any other weird stuff. I want to kind of build a board for the 8080 and 8085. I've got some S100 emulation planned, so I've got a lot of stuff in the works, and only so much time.
Looking at the architecture of the V20 and the, compared to the original 88, do you have any insight of why Intel did or did not react to it? Because it looked
Well,
like
I mean, they were looking at more like the 186, taking the stuff that Intel did from that. Obviously, the 186 instructions, but you mean why didn't Intel make a better 8088 themselves?
Yeah, because it's still used
I think they were
everywhere.
just all in on the 286, and they just didn't care. I'm not a historian, so I can only speculate.
But I'm sure there's still stuff using the 8088 today.
Yeah, probably somewhere in some industrial machines.
Yeah, we were using it in some products we had like over 10 years after it was released. We were still producing products, and I'm just saying Intel was shipping it. Why didn't they?
The real fun
Put
thing
any-
I'd like to do, or have an opportunity to improve emulation, is the V20 has an 8080 mode, right? But most emulators for the V20 just kind of like don't bother with it.
Mm-hmm.
So I'd like to have full cycle accurate emulation of both modes of the V20 too.
Okay, thank you.
You're welcome.
Any other brave soul out there? This way.
More on V20. Obviously, V20 has a number of instructions that are above and beyond the 8088, in addition to the 186 ones, but all of its own, homebrew proprietary ones. In the event that you want to do a V20, V30, et cetera, without having a Ken Sheriff decap and map, is there any clever way you'd be able to get the microcode for the non-Intel instructions?
Well, hopefully they have like a static execution time, meaning they're not executing in different amounts of time depending on how you run them. A lot of the instructions, if they've just got one execution time, you don't need the microcode. You just cheat and return the number of cycles. Yeah, it just depends. I won't know what I don't know until I start trying it.
Right.
But hopefully it's similar to the 186, which we do have the microcode for.
Awesome. Look forward to it.
Anybody else? Then I'll ask a question. Have you ever tried putting a faulty 8088 in and seeing what kind of blather you get out of it?
Well, when I had that Intel 78, I thought it was broken because it was running. I figured that it wouldn't run at all, it being NMOS, if it had a problem.
Mm-hmm.
So I was kind of banging my head against the wall. I thought it was a bad chip because I put my AMD in there, still NMOS, and it worked fine. I was like, oh, bad CPU.
Okay.
But I later just decided to put that Intel in my 5150, and it booted right up. So I was like, well, wait a minute.
Doo-doo-doo-doo.
Yeah, it would make a good CPU tester if you had, 2 weeks to test each CPU.
Yeah. Okay, with that, any other taker? All right, give it up for Daniel Balsom.
Thank you.